So on Sunday, it's going to be big snow, so we canceled that day. Otherwise, some chocolate will be trouble. Anyway, so I hope you will exchange ideas with other people, and anything that you need, send the help, let me know. And David Gu is going to start the conference.
Okay, thank you everyone for coming for this workshop. Really appreciate your support. Okay, so we have invited a lot of world-renowned speakers. Okay, so today we start with Professor Donghui on the topic for random projection forest. Professor.
First, I would like to thank Professor Yao and Professor Gu for the kind invitation. And also, I want to thank all of you for coming here, despite the cold weather. It's truly a great honor to speak at this workshop. So I'm going to talk about a tool which I developed during the last few years with some of my colleagues. So this tool is for random projection forests. So I will talk about, first I will briefly introduce random projection forests. Then I will introduce two applications. Actually, there are more applications I could develop. So random projection tree is an ensemble of trees constructed recursively on random projections. So it combines the power of ensemble methods and the flexibilities of trees. So the main use of these random projection trees is it can help discover patterns or properties deeply hidden in the data. For example, locality, which is potentially useful for many applications. So first, for those of you who are not familiar with trees, so I want to say a few words about the tree-based methodology. So it's a broad class of methods in statistics, data mining, and machine learning. Some of you may have heard of those tools like SQL 4.5, CART, random forest, gradient boosting machine, and it has a huge impact in many applied areas. For example, medicine, finance, commerce, and potentially in every field. So one bigger advantage of tree-based methodology is the faster computation. So the tree construction takes about big O, N-O-N computation, and the search and prediction takes about log n. So this log n constant is related to the height of the trees. Okay, so typically tree-based methodology has a decent performance, and it's good for interpretability. Resembles human decision dichotomy. Okay, so I will show this slide. I will show you a simple example of tree-based methods. So suppose we have those data points in a unit square, and those different points they have a label. For example, those 0 belongs to has a label 0, or others they have a label x. So now we want to construct a tree that can separate those 0 and the x. So how are we going to do it? So first, it will select some variables, for example, x1. So then it will calculate at which point I want to split the data. Okay. So suppose this is the point it selects, which is optimal according to some metric. So it split the data into two halves. Okay. Accordingly, in the root node we have all the data. After the first split, so that let's see. Left side, all those data points has the x1 coordinate less than 0.7 goes to this. The other data go to this right child. Okay. So for this part, this child it will continue the similar procedure. So for example, it's the next time we choose the second variable to split the data. Okay. Say this is x2, and then decide x2 equals 0.5 is the best splitting point. Okay, so keep on splitting the data point until there are some stopping criteria. So after this, so we get this partition of the space, and you can also view this partition of the space as a function. So in what sense? So for each data point in the same leaf node, we're going to assign the same value. So you can think of this as a piecewise function. Okay, so from this, the tree construction, you can actually see that at each tree split, it actually uses some information from the label, okay? From the label or from the response variable. So you probably will be wonder, what if you don't have those labels? Or in other situations, if the labels are very noisy, okay? So what are you going to do? So, so that is, you want to figure out a way for this unsupervised learning mode. So how to grow the tree? So one simple strategy is actually to randomly split the node. And the resulting tree is called this random projection trees proposed by Dartmouth and Fuyang in 2008. So, so this is a simple illustration of these random projection trees. So first, it randomly pick a direction to split the data. So this is a random pick the direction. So at this, for example, in this node, it randomly pick another direction, which is this one. So split the data into two halves and keep on going until eventually we have those end up with those leaf nodes. Okay, so that this is the random projection trees. Okay, so this is how we the projection actually works. So suppose we choose this as a direction. So first we project all the points onto this line. So then we will randomly pick a point to split the data into two halves. Okay. So it's very simple. So probably the very natural question is this. Maybe this. You'll probably be wondering, does this thing work? Because the tree growth seems very random. Actually, there are some quite a few evidence. For example, theoretical evidence provided by Dartmouth and Fuyang. They actually show some nice properties of this random projection trees. For example, they show that the radius of the tree nodes shrinks steadily with depth. And there's also empirical evidence. For example, in the method which I proposed with my friend Huang and Jordan in 2009. So we actually, we wanted to speed up this spatial clustering, which usually takes about the cubic complexity. So how to speed up the computation? What we did was this. So we group the data by the data and its neighbors. Okay. So then we compress those data in the same group, treat that as one point. So then we are going to apply this spatial clustering on those compressed data points. Okay. So then we use this to interpret the clustering membership for all the data points. Okay. So we actually show this show that by doing this, you don't lose much, or sometimes you actually get a better performance than if you work on the entire data set. Okay? But the advantage is this, because we do this very expensive computation on this very small data set. So that was about 10 years ago. So that time, if you do this spatial clustering on 10,000 data points, it probably took about one whole day. So what use this, the algorithm we developed, we actually can do this spatial clustering on 1 million data points within 5 minutes on laptop computer. So the idea is this, why this works, because even if we do this grouping, it doesn't affect only those points affected are near this boundary. So this actually works, although we use these random projection trees. So those are the data points that are in the same leaf nodes. Okay, so in spatial clustering, it actually works. So however, there are, if you want to, you probably want ask another question, does this work in some other application? For example, if you care about the so-called locality of all the data points, that actually doesn't work. So I tried this because, so I tried this on this very important application called k-nearest neighbor search. So I tried it, I found that the performance wasn't so good. So then I figured out the reason was this, because the result depends on the point-wise locality of all the data points, not just those data points near the decision boundary. So in that case, you want to have something better than these random projection trees. Or otherwise, if you have random projection trees, after that, you need to do some small fix. Okay, so the idea is this: why this doesn't work? Because those data points, the locality was actually compromised at near the leaf node, near the node boundary. But those are actually not. This only created by the trees, not the problem itself. Okay, so one strategy actually to make this work is actually to use ensemble. So basically, we group many different trees. Then we're going to aggregate the result from many different trees. So in that case, those locality compromised in on one tree will actually be compensated in from other trees. So if you group many of those, that can actually tell you this preserves the locality. So actually we prove this a very simple result. So if you have a set of data points, then if you group the tree using these random projection trees, they actually have a very nice property. So the property is this: if you have two data points, so if you have two nearby data points which are very close to each other, so even if you do this group the tree seems to be seemingly entirely random, the probability that these two data points get separated has a probability outbounded by this. Okay, so this formula looks a little complicated, but actually it has nice interpretation. So this is the number of trees. So that means if you have more trees, if this number is small, you get the probability will be very small. Okay, so this is desirable. This is good. Another thing I think which is nice is this one constant, a particular constant, which is useful is this number called this mu. So what is this mu? Mu is actually this so-called, I call it the next size. Just imagine this bottleneck, the weakest part of the data set. So usually people talk about this principal direction, right? So it's the direction which the data stretches the most. So this next size is actually the amount of stretch along this so-called minor direction. So it's the direction that the data stretches the least. That is actually the weakest part of this of the trees. So later on, I'm going to we actually use this property. This actually help us to refine our design of this random tree. We make it slightly less random. How to do that? Instead of choosing this random direction to split the data point, we're actually we prefer to split the data point around those directions, not this direction. Because if you split around this direction, they will create those thin long slices, which is not good for this locality. Okay, so that is the property of these random projection trees. So there are a number of related works. For example, random forest, random projection trees, and all those this supervised mode. And there's also unsupervised mode, which is called class forest, which I developed with my friend Chen and Jordan a few years ago. So we grew many. So that was for the clustering application. So we grew many different clustering instances by the idea called this randomized feature pursuit. Okay, so we view that as an unsupervised extension to random forest. We can also view these random projection trees as an unsupervised extension to random forest. And since this is at the math center, I want to mention another related work, which is related. I think it has deep roots in pure mathematics, which is called Johnson-Linus-Strauss lemma. So which says you have a very high dimensional data cloud. If you want to project those into a very low dimensional space, so the separation, it actually preserves the separation with very high probability. So that is the Johnson-Linus-Strauss lemma, which was originally proposed by some pure mathematicians. Later, people in machine learning and computer science found some applications of this result, and later that result inspired the entire field called this compressive sensing, and also many development around this line. So now I want to talk about one application of these random projection trees, which is the k-nearest neighbor search. So we know this k-nearest neighbor search has wide applications in data mining, for example, used for similarity search. So you want to search some items close to a given item in some database, or you search on some website. Okay? In machine learning, we use this k-nearest neighbor search to specify the similarity matrix or the ground matrix for faster computation. In statistics, k-nearest neighbor also used for number of applications. For example, the non-parametric or data-driven density estimation, or k-nearest neighbor based hypothesis testing, or intrinsic dimension estimation, and also in this applied area called anomaly detection. So many different applications. Okay, so the one problem of this k-nearest neighbor search is this: if you do this in a naive implementation, it actually takes n squared, has an n squared computational complexity, which is not feasible if the number of data point is huge. Okay, so there are a number of algorithms have been proposed. For example, there's cover trees, locality sensitive hashing, so which is a very important work. I think this India is currently at MIT. I think. So the idea is actually to design some function and map all those data points to a function. So use this. If those data points map to the same function value, they treat those as one computational unit. But the problem is you have to come up with a function which actually reflects the property of the data, which is not easy. And also there are randomized KD trees. So in this case, the tree construction also random, but the direction not entirely random. It's randomly pick one direction according to this one of the coordinates. It's not entirely random. So in that case, it actually suffers from the so-called dimensionality curse. If the number of features is huge, so this method doesn't work. And of course, there's random projection trees. So this Dasgupta and his students, they proposed some extension of these random projection trees. So on a single tree, so they route the data to multiple diff nodes, just to compensate the potential loss of locality in one of the diff nodes. But it's the implementation is not easy. Okay, so this is the random projection trees. You can see that, for example, we're interested in this data point A, and those are the nearest neighbors. Okay, so during this tree growth, at some stage of this node split, some of those nearest neighbors actually got split. Okay, so eventually we see this. Most of those nearest neighbors actually end up in the same diff node, which is good. Okay, because eventually we're going to do the k-nearest neighbor search on these three different nodes. But those data points those should be the k-nearest neighbors, but they are actually lost because of the boundary created by this the nodes. Okay, so this if you use this random ensemble of this, which we use the random projection trees, so that actually the search will actually be conducted on this, not just this node. Suppose you have nodes like this, so you're going to search on a union of those different nodes. Okay. So we did some experiments on this, on the accuracy and also the computation time. So we have two performance metrics. One is the percentage of data points which are missed in the k-nearest neighbor search. Another one is the distance, is the k-nearest neighbor distance. So because of the miss of some of the near neighbors, the distance you find actually may not be exactly the distance computed by the brute force. Okay? So we want to see how much loss you have. So we try a number of data sets from the UC01 machine learning repository. So this data point has features from very low, small number of features to up to more than 10,000 features. These are actually the image data set. Okay. So you actually see that when you increase the number of trees, the missing rate quickly decreases to 0. So at around 40 or 60 trees, the missing rate quickly decrease to 0. Okay? So those for all those different data sets. And these two are for the distance. The distance quickly converges to this the distance you get by brute force. And of choosing this random direction, we try to cut around this direction which the data stretches the most. So how to do that? We try this. So at each time we want to split the tree node, we choose a few directions, and we calculate the standard deviation. We then choose the one with the largest standard deviation, because then the standard deviation actually is the represent the amount of stretch. Okay, so we also did some simulation. Okay, so you can see that. So this green curve are the random projection trees using only one direction. So this is we use 3 directions. So every time instead of choosing one direction, randomly split data set, we choose 3 directions and then use the one which has the largest standard deviation. You can see that the error rate quickly decreases. So that actually shows that this is the theory we prove actually help us to refine our methodology. As I said, we also did some experiment on the running time. So because this the random projection trees is an ensemble of many different trees. So those trees can grow independently. So we actually tried this on these multi-core computers. We tried this computer with 2 cores and 4 cores, with the instance number of data points from a few thousand to a few millions. Okay, so this is the result. So this is this is the result for 4 cores, 2 cores, and this is the result the time for by other methods like cover trees and other methods. So in most of those data sets, so we have this lowest. So these 2 are the result by random projection for us. We have the lowest computation time. Okay, as I said, I'm going to introduce another application, so which is in the scoring of tissue microarray images. So tissue microarray images they measure this tumor-specific protein expression level. It's very useful for cancer studies and also for this number of applications like validations of biomarkers, study of genomics, a number of applications. So those tissue microarray images, for those of you who are not familiar with those, these are actually related to the tumor. So take from the patient body, so with a small punch, so something like this. So you can think of that as a cylinder, very small, with very small radius, like a few millimeters. So then you arrange this on a piece of slides, a few hundreds. So then you apply this so-called biomarker, different solutions specific to a particular tumor or particular cancer. So then under this microscope, you take these images. Okay? Each of these correspond to one image. So how to use these images? Usually, those pathologists we actually assign these scores based on the color. So those, if there's a tumor, then by applying this biomarker, they will actually show dark color. So those scores are related to the darkness of the color and also the percentage of the image that shows this dark color. Okay, so a very popular scheme is this: they score the images in 4 levels, from 0 to 3. 0 means it's definitely negative, it means healthy. Okay, 3 means it's a definite positive. Probably at you can imagine that as the later stage of cancer. Okay, so the challenge of this is actually for images with different scores, they look so different. It's very different. So it's so different. It's very challenging to this to do this scoring. So a number of methods have actually been developed, because if you ask the pathologist to score those images, there are several problems. For example, variability, subjective, and also labor intensive. So different pathologists may assign different scores. Even for the same pathologist, they sometimes assign different scores for the same image at a different session. So we actually did some experiment. The so-called self-agreement is actually quite low. It's between 75% to around to 84%. Okay, so you can think of it as 80%. So that actually calls for the development of automatic algorithm. But you see that automatic algorithm, because those images with the same score, they look very different. So how to do that? Our approach was actually to try to use those statistics. There are some statistics, although they look quite different, but some kind of image statistics are quite stable. So in particular, we use this so-called the grid level co-occurrence matrix. So you can think of that as the histogram around certain direction, a spatial histogram. Okay. So each image then will be corresponding to one matrix, something like this. For example, this is the image, and we extract those image statistics in the form of this matrix. Okay. So in this matrix. Okay, so that's the method I developed with some of my colleagues a number of years ago. So we wonder if there's any chance we can further improve the results. So how are we going to approach this? So we start from the difficulty or the challenges in the image scoring. So we actually found out the images are very noisy. Okay, very noisy. That means the labels, sometimes even if they give a label, the label may not be reflect the truth. So that's our starting point. And then we use this some inspiration from the deep learning. For example, we wonder if it's possible to discover some representations that are not obvious to the humans, but you can discover that by computation. So we actually find out it's actually possible, and we call that algorithm called this deep Takuma. Okay, so this algorithm works by so this is the idea, as I just mentioned. We find out the labels are quite noisy, and we want to enforce this one particular idea. What is the idea? Similar images, they should have similar label. Okay. Sometimes if the similar images do not have the same label, that means then potentially there be some mistake. So we want to enforce this, and this is actually the similar idea of this regularization in statistics and machine learning. So how are we going to do that? We try to group those images. If they are similar, we put them in the same group. Okay, in the same group. So how to find out those similar images? We actually compute that by these random projection trees. So if the two images are very similar, then they will actually meet in the same leaf node in many trees. Or in other words, the similarity will be very high. Okay, so that is the idea. So basically, originally we have some images. This is the so-called grid level co-occurrence matrix, the spatial histogram. Then out of this histogram, we produce additional features. So those features actually correspond to the group ID. If two images in one tree they fall in the same diff node, then you on this one of these additional feature, they will have the same feature value. By appending these additional features, we enforce this idea. Similar images should have same labels. Okay, so this is the idea. And we did some experiment on the same set of images we did before, which is the TMA images correspond to estrogen receptor, so which is correspond to this breast cancer. So previously our result was this. The error rate was around 24.79%, which is already quite good, because the self-agreement for the pathologist is between 75% to 84%. So this is in the range. Okay, we did some experiment. We actually used different ways to enforce this grouping. So we use this k-means clustering, hierarchical clustering, ensemble many different versions of hierarchical clustering, also random projection forest. So it turned out random projection forest can lead to some improvement, further improvement. So you probably see the value, in absolute value, the improvement was not big, but because it's already quite close to the trained pathologists, so it's we think that we ask the pathology, they think this is significant. The improvement was significant. Okay, so so we wanted to. So usually in statistical the machine learning, after you propose some methodology, it's very natural to ask, do you have some theory? So in this particular case, we don't have a theory, but we can alternatively is we actually can run some simulation. In those cases, we know the data distribution, we know what we expect, and then we want to see if the method produces those expected results. Okay, so that is what we did. So we tried three different set of experiments. One was for this mixture data, which says the data has different, which is the mixture of Gaussians. Okay, so that is actually for the data with different labels. Another experiment which is the so-called heterogeneous data. So in that case, the data is still generated by Gaussian. But if the data come from this different mixture, for example, the first mixture and the second mixture, they have the same label. Just to resemble this, the idea of this, you probably see this. Those images, they have the same label, but they look very different. We call this heterogeneity. So we use this Gaussian mixture to actually simulate this scenario. So actually, you can see that in all those different scenarios, those idea of this random projection forest indeed leads to some improvement. Improves the most when there's a moderate. So those are the label noise. Rho is the label noise, means 0.1 means 10% of the data points we flip its label to a wrong label. This means 30% of the data point or the images we flip its label by a wrong label. So it turned out when the label noise is moderate in this range, the improvement was the most. So this means you don't do anything, any of these additional features. That's the error rate. So those are the error rate we get by appending these additional features that enforces this the similarity. So we have this improvement. Okay. So in different scenarios, the first one is this the simple case. Second one is the heterogeneous data. So we still get this improvement. Okay, improvement. So the third simulation is this for very high dimensional data. Also similarly, we get this get some improvement in the performance. Okay, so this final slide basically just to tell you the scoring of this TMA image is very hard. So this image, this figure, we actually show this for each feature. We show that the features, how many features are highly correlated to this particular feature. So the idea is basically to show you this. The features in these TMA images, they are highly correlated. That actually create a problem or difficulty for developing statistical or machine learning algorithms. Make it very challenging. So this actually shows that for each data point, the number of other features which are highly correlated to this feature is very high. Okay, so basically show it's difficult. Okay, so to summarize, we propose this method called this random projection forest, combines the power of ensemble method and the flexibility of trees. It's a versatile tool, can be used for a number of different applications. So here I just list two applications. Actually, we have come up with some additional applications. Probably in the very near future, you probably see our results. In some other applications also show very promising results. So the random projection forest can run on multi-core or cluster computers, which makes it very ideal for this handling large data sets. Okay, and thank you for your attention.
Oh, we have question times. Okay, we have 25 minutes for questions. Any questions for the speaker?
These random projection trees, how would they compare to something like locality-sensitive hashing?
We didn't compare it because we couldn't find this the code for this locality sensitive hashing.
But more actually on an idea point of view. I mean, I think of locality-sensitive.
Yeah, the fundamental idea was the same. Basically, you want to group the data in using different ways. Locality sensitive hashing does this by a function. If those data points map to the same function value, they treat those data as a group. In our case, if those data points fall in the same tree leaf node, we treat those as a group. So it's probably I would see this. Our method probably is more data driven because the tree, the eventually how we get the tree growth depends on the data actually. We didn't do the comparison with locality sensitive hashing. Sorry.
So, what was your reference about Johnson-Lindenstrauss? How does Johnson-Lindenstrauss relate to your
It's
work?
basically says this. So in our case, the projection was projected to the one-dimensional space. So even though all the data points are projected to this to a line, so still you see that there are some properties that are inherited from the high-dimensional space. So in what sense? You see that, for example, those data points that are close, the projected data points are also close. If this data point is very close, are very far away from this projected case, they are also very far away. But of course, if data points are very far away from this direction, that's not the case. But then we have many different versions. So the intuition is that by we sort of inherit some properties of the high-dimensional space using many different versions. Then we aggregate. That actually help us to reconstruct the properties in the regional high-dimensional space.
Okay.
More questions? So could you explain the conjecture in more details? The conjecture you mentioned. The conjecture.
What is the conjecture?
So some mathematician reason conjecture.
It's not a conjecture. It's a lemma. Johnson-Lindenstrauss.
That one was the result. It's Johnson-Lindenstrauss lemma.
A lemma.
Yeah,
Okay.
by the way,
It has
this,
been proven. Has it been proven already? Or-
It is proved. It's
Oh,
proved.
okay.
So there actually originally it's proved. From what I know, I probably may got it wrong. Proved in topology or maybe in topology or maybe some pure mass field.
Okay.
Lindenstrauss actually, for those of you who are in the pure mass field, his son actually got the Fields Medal in the last few years. So,
Could you explain the lemma?
the lemma basically says this. So the lemma imagine that you have data point in this high-dimensional space.
Some chalk and
Yeah. So imagine that those data. So this is a data cloud in a high-dimensional space. Okay, very high-dimensional space. Now you project to some low-dimensional space. Okay. So the lemma basically says that it preserves the separation of the data points. So a particular case is you can think of this as a high-dimensional Gaussian mixture. The separation is usually measured by this the mixture center. Okay. In high-dimensional space, they have this separation. In low-dimensional space, it preserves this in high probability. It's not deterministic in high probability because you can randomly project to any space. So with high probability, it preserves those separations. So those are the data points in a low-dimensional space. Okay, so those are data points in low-dimensional space. So that's the center. So the center, you see, still they are still quite far away from each other. So that's the result.
But, I mean, it says actually more than that. It actually says that there's a Lipschitz map
Lipschitz map.
from high-dimensional space to low-dimensional
So
space.
do they assume that the point cloud has manifold structure or anything?
Yeah, no, you don't have to assume anything about the high-dimensional space. The only thing that actually comes in the bound is actually the number of points.
Okay.
So that's why it's really powerful. It's a very general statement.
So is there any relation between the random projection tree to manifold embedding or manifold learning?
Manifold learning actually it helps discover this so-called group property. So I know you are interested in this manifold structure. It's I would say it's related to that, but not exactly. So both this manifold structure and this group structure are those deeper latent structure of the data. Maybe I would say it's fair to say it's parallel to the manifold lineage.
Quick, more questions? Okay.
Just if you look at images, can you do a random convolution with random?
Yeah, you can try that. Yeah, random convolution. Yeah, yes, that's another idea. Yeah. You can try that. Okay, we didn't try that. Yeah, you can think of this random filter as this some kind of projection. You can think in broad sense.
So, but if you take the feature vector at different layers, do you think it can have different? Which one do you think it would be the best? The last one, or the last layer, or
In this in terms of image recognition. Image recognition from this deep learning. There are some results in deep learning. They basically say that there's a hierarchy. It actually learns the hierarchy of these image features. For example, in the first few layers, the first layer, the input was this pixel level. The second layer of this deep neural network, they learn this texture structure. So as it moves to the later layer of this deeper network, it becomes more and more close to the actual object. Then it comes to this object parts. For example, if you look at the picture of myself. First, you look at those single pixels. Then you see this the textures. Then you probably see small parts like these eyes, ears, nose. Then probably you see a head or body. Then eventually you see this the whole picture. So I would say probably the later layer probably will be more effective than this than the first few layers.
do you expect that you can do that with the random projection, or does it have?
Random project, I'm not sure if that can achieve that. Probably you need to do a lot of post process. After you do this random projection, you need to aggregate or fix some of those results you get from the random projection. Just my imagination. I didn't try that.
Yeah, you mean your program RT4 can run on multi-core laptop? Yeah, but can it run on multi-load cluster?
Yeah, of course, it's a similar idea because you see that the growth of those individual trees are entirely independent. So because it's randomly grows, the growth of one tree does not affect the growth of any other trees.
So you use MPSH or?
Oh no, we only tried it in the multi-core computer.
Oh, only multi-core.
Multi-core, but the same. I believe you can similarly you can do it on the clustered computer.
But the parallel mechanism is different between.
Yeah. So in this case, it's actually easy because the growth of individual trees they're quite independent. So you don't need this frequent communication between different nodes or different computers. You don't need this communication. You only need to collect the result after you finish the construction of the trees. At the final stage, you collect those results, you aggregate. Only then you need to communicate once. So I would say implementation wouldn't be difficult.
Okay, it's written in Python or C++.
In this case, I wrote the R version. Then some of my students actually ported it to this RCPP. RCPP.
More questions? Okay, let's send the speaker. Okay, the next talk is scheduled at 10, so you can have a tea or coffee.
안녕.
How did you get it?
Those are different. Those are yeah. We combine it, append this. So originally, for example, we have 2600 images. Then we append those features from the random origin trees as this additional, let's say, 400 or 500 features.
That works.
Yeah, that works. That is actually an easy way to incorporate this result. Yeah. Send me email. So I will send you. I can send you. My email is gyan@UMass. UMass.
对，还有一毛都是看他们
Thank you.
那就是可能是用相对的这个或者用中等化来做这个。
Oh, we have not published our code yet. Yeah, in the near future, maybe in the next few months, we're going to release our code. Potential application, basically, so you can see that, it can apply to any application that has this, for example, you have this, you have those clustering structure in the data. For example, in semi-supervised learning, that's another potential area. I wouldn't say completely replace that, but it's because it's very fast. Random forest, because at each tree leaf node, it actually does some computation. So this is much faster. How fast so for example, if you have a data set in the previous neighbor search, million data point probably take like I don't remember, maybe a 400 seconds or something. I don't remember exactly. Yeah, it also depends on how many cores you have. So we only try with 2 cores and 4 cores. We don't have more advanced machine.
研究人的族谱，就是forensic， 就
Yeah, they actually for different purposes.
推出这个人脸，然后3人脸。
准不准啊？
其实主要现在可能还是用学习的方法吧，然后
真的很好。
比较应用的。It's more private, there's no deeper mathematics.
可以去以外其他的 program。你看是要用去，用 more complicated
More complicated is possible. Tree is actually